Hello everyone.
Okay.
Today in Young-HOM we have Sheaf from Bonn, who is going to talk about fractured structures on condensed anima.
Yeah, thank you for letting me speak in the seminar. Yeah, in these days where condensed mathematics is so hot, we thought it'd be cool to contribute a little more to this world of condensed mathematics. And this talk basically arose from my master thesis project, in which my supervisor was Nima, and this project is also joined with Nima and still ongoing research. So it's about a fractured structure on condensed anima. And let me start off, where does all of this come from? Where does this arise? And the tale all starts in topology. So I want to say, in this kind of setting, I probably don't have to convince you that topology is not only basic, but it's also ubiquitous. It arises everywhere throughout mathematics and beyond. To just quickly mention some examples, early on we studied the extreme value theorem or the intermediate value theorem in our first calculus classes, and they of course hinge on the notion of compactness and connectedness, both central notions of topology. And it's ubiquitous, it appears everywhere. To just mention some basic examples in algebraic geometry. People learn about the Zariski topology and number theory. We use different kinds of p-adic topologies, functional analysts endow their spaces with different kinds of function space topologies, and probability theorists use their sorts of polar spaces. And there are, of course, numerous other examples that you can add on to the list. So it's such a basic and ubiquitous concept and field, but nonetheless, topology can be flawed. And let me mention two areas in which this can happen. So the first area I want to say is algebra. And very often one wants to try to marry the idea of algebra with other kinds of structures, such as a topological one. And maybe the easiest concept that can arise is that of a topological abelian group, or the category of topological abelian groups. But it turns out that this has a fatal flaw, namely this is not an abelian category. And this can be seen, for example, by considering the identity map on underlying spaces, where we take the real numbers and dealt with the discrete topology to the real numbers and dealt with the Euclidean topology. This is trivial kernel and co-kernel, but it's not an isomorphism. And so in this category, a priori, you cannot perform homological algebra. So this is a flaw with this category. And the second field I want to say is that of homotopy theory, which is of course important nowadays, in which fields like homotopy type theory and higher categories are on the rise. And so homotopy types become more important than ever. And homotopy types can typically be modeled with actual spaces. So like CW complexes or COM complexes, but passing to their homotopy types, it simply forgets way too much information, forgets all of the topological and geometric information of a space. For example, the unit disk represents the trivial homotopy type. And so this forgets a lot, and it's another problem with homotopy theory. And so all of these, they prompt a quest for generalization or axiomatization. And I want to present two possibilities to do so. The first of these is condensed mathematics. And the second of which is that of a cohesive and of a fractured topos. So these will be two notions which will somehow recover some notions of topology that will be more general and more axiomatized than the usual notion of a topology. And then in the end, we want to compare what kind of notions are interrelated between these two. Okay, to start off, let me start with condensed mathematics. And I want to define or recall what condensed math actually is. And condensed mathematics really hinges on a notion of topological spaces, so three really nice subcategories of topological spaces. That is, I want to consider the category of extremely disconnected spaces, which sits fully faithfully inside the category of profinite sets, and this sits fully faithfully inside the category of compact Hausdorff spaces. So C-house, as this terminology suggests, these are the compact Hausdorff spaces. Profin, these are also compact Hausdorff, along with the additional property that the spaces are totally disconnected. And as disk, these are also compact Hausdorff, together with one funny property, namely that the closure of open sets is always open. And it's a point set topology exercise to show that this is really a full subcategory of profinite sets. On each of these three categories, we endow a Grothendieck topology that we'll call tau Koch. And those are given by the finitely jointly surjective families of maps. So a sheaf is a collection of maps over an object such that there is a finite collection which jointly surject onto the object. And the definition of a Grothendieck topology, it immediately prompts taking sheaves. So that's what we'll do in proposition 1.2. Namely, we can take anima valued sheaves on compact Hausdorff spaces, where anima is a synonym for the infinity category of spaces or groupoids, infinity groupoids, and so on. And you can restrict sheaves on compact Hausdorff spaces to sheaves on profinite sets to obtain a functor to the sheaves of profinite sets. And this again, you can restrict onto anima valued sheaves on extremely disconnected spaces. Now, what we want to say is that these are equivalents of categories. In the one categorical setting, this would already be true. But in the infinity categorical setting, there's a slight technical aside that we have to add, namely that we need to take the hypercompletions of these first two categories. The third category is already hypercomplete, so this is not necessary here. And then this leads to the definition of condensed math, which is attributed to Dustin Clausen and Peter Scholze, and at the same time, Clark Borwick and Peter Hain. Namely, a condensed anima is a sheaf on extremely disconnected spaces. Now let me briefly mention that these things are nothing to be scared about because they admit a very concise description. This is lemma 1.4. So let's take one of the three essential categories we're interested in: compact Hausdorff spaces, profinite sets, or extremely disconnected spaces. Then a functor from C op to anima is a sheaf if and only if it satisfies the two following properties. First, F preserves finite products. And the second is, for every surjection in one of these categories, the check nerve induces a limit diagram.
Sorry, there is a question in the chat. In proposition 1.2, is the first thing an equivalence if without the hypercompletion? Just the first equivalence, does that hold?
I'm not sure. Okay. Probably not. I'm not sure, sorry. Thank you for the question. Okay, so to come back, a sheaf, a functor from C up to anima is a sheaf if and only if it satisfies the following two properties. And you might realize that the second property does not always make sense for extremely disconnected spaces, because extremely disconnected spaces is kind of not a well-behaved category, as in it does not have all limits. But on the other hand, it's also really cool for condensed stuff, because if we're looking at extremely disconnected spaces, then this condition can be omitted. So a condensed anima is the same thing as a free sheaf that preserves finite products and nothing more. Okay, and one can try to pass to this new light setting that Peter Scholz and Dustin Clausen have been introducing in the lectures these days. But it's not something that we will be doing in our setting for now, because extremely disconnected spaces are important for our work and do not really admit the light structure that they're working on. Okay, this is all I want to say about condensed mathematics. Let me go on with cohesion. And cohesion, I want to motivate via one central example, namely that of topological spaces and of sets. And we can take the forgetful functor from topological spaces to sets, and this always admits both adjoints, namely by taking the co-discrete or indiscrete topology or discrete topology. And if our spaces are nice enough, so something like locally path connected, then this admits another fourth adjoint functor, namely the path component functor. So this is already a quadruple adjunction, which is pretty nice, and the functors are even really nice. So for example, pi naught preserves finite products. And the discrete and co-discrete functors, they're fully faithful. And cohesion is precisely an axiomatization of this example. The definition. This was first introduced by Lavere and was generalized to the infinity categorical setting by with Schreiber. Namely, let X be an infinity topos over an infinity topos y via a geometric morphism f lower star from x to y. So it admits a left exact left adjoint. Let me also mention that the definition can be done a little more generally so that the above thing makes sense, because topological spaces does not form a topos. Then x is called local over y if there exists a triple adjunction between these two guys. F upper star, F lower star, and F upper shriek, such that also F upper star and F upper shriek are fully faithful. And it's abstract nonsense to show that it suffices to demand that one of these is fully faithful. And X is called cohesive over Y if X is local over Y, and there exists another fourth adjoint functor, which is furthermore finite product preserving. So all in all, this is a diagram of the following form. We have our two topoi x and y, and we have these four functors which are adjoint to each other and satisfy nice properties. Okay, this is a relative version of cohesion. I don't want to use the relative version of cohesion to pass to an absolute notion of cohesion. And for this, I want to do the following. So if we start with any infinity topos, x, then there's always a natural map from this topos to the infinity topos of anima, namely given by global sections gamma. So this is the Young-HOM functor, so the mapping space from the terminal object of this infinity topos. And it turns out, so by the adjoint functor theorem, it always admits a left adjoint, namely the discrete functor. And using this functor, we can now define cohesion absolutely. So again, let X be an infinity topos. Then X is called a local infinity topos if X is local over anima via this map gamma. And in the same fashion, X is a cohesive infinity topos if the global sections functor is cohesive. And here's a little bit about notation. If X is a cohesive infinity topos, then people like to use the following notation for the adjoint functors, namely uppercase pi, discrete, uppercase gamma, and co-discrete, which is similar to the beginning example that we give. So gamma should be something like the underlying space or global sections functor. Discrete and co-discrete is something like discrete or co-discrete cohesion or topology, while pi is supposed to admit to have the homotopy type information of our topos. Okay, and to end the cohesion part, to convince you that these guys are cool, let me give you some examples that arise in homotopy theory. Example 2.5. If C is a small pointed infinity category, and Y is an infinity topos, then one can show that the functor category from C to Y is an infinity topos cohesive over Y. And this gives us a lot of interesting examples interesting to homotopy theorists. So for example, when we put Y as the infinity topos of anima, then we recover a pre-sheaf categories of C. If we put C as the category of finite sets, of pointed finite sets, then we are in the setting of gamma objects. So this, along with some conditions, gives us gamma objects. And if we put C as the pointed finite anima, then we're in the setting of good Billy calculus. All of which are interesting to homotopy theorists. And here's another family of examples that should not be missing for homotopy theorists. Namely, if Y is an infinity topos, then the simplicial objects in Y, of Y, so the functors from delta up to Y, this is cohesive over Y. There's something that one can show. So for example, simplicial anima is then a cohesive infinity topos. So these are a lot of examples that show up in everyday life, which are cohesive. And that's all I want to say about cohesion. And let me turn to fractured structures, which is something that, well, cohesion is really nice, but sometimes life is not nice and things are not cohesive. And the thing that we pass to is fractured structure. I want to tell you why fractured structure is an alternative to cohesion. So this is a notion due to Carcetti and Lurie that you can find in his special algebraic geometry. And the definition itself is rather technical, so I've written out most of it, but let me highlight the important parts. We start with an infinity topos X. Then a subcategory called X corp. So these are the corporeal objects. This is called a fracture subcategory. If it satisfies the following four properties. So one is if we start with any object that is corporeal and take an equivalence that starts in there in X, then this morphism is already corporeal. The second is that X corp has pullbacks, and these are preserved by J lower Schrieg, the inclusion functor. The third is pretty central to our doings, namely that there is an right adjoint to our inclusion functor J lower Schrieg that we'll call J upper star. And this adjoint is pretty nice. So for example, it's conservative and it preserves small colimits. And then at long last, there's a fourth condition about some pullbacks. So for every map in X corp, the co-unit induces a square, and this is always a pullback in the initial category X. Okay, and then a fracture infinity topos is a fracture subcategory of an infinity topos. So all of these conditions, they arose from algebro-geometric settings in which Lurie and Carcetti discovered that certain things hold, and then they axiomatized these conditions. But for us, many of these conditions actually are not too relevant. So for example, there was recent work by Sol, Tobias, and Bastian, which uses fractured subcategories in equivariant homotopy theory, and they use this condition 4 in an important way that we do not use. But for us, we have the viewpoint that fractured structures locally give us cohesion in the following sense. The remark, fractured structures locally almost yield cohesion in the following way. So we have our topos or we have our subcategory X corp, which sits inside X via the functor J lower Schrieg. And this admits by condition 3 a right adjoint J upper star. Which preserves small colimits by condition 3. Now one can show, as is done in Lurie's SHG, that X corp is also an infinity topos. So we can apply the adjoint functor theorem to obtain another right adjoint of J upper star, or J lower star, the adjoint functor theorem. Now, let us take an object which is corporeal and slice the entire diagram over this corporeal object. Then it turns out, as one can show, that this diagram becomes even nicer. So for example, J lower Schrieg is fully faithful in this setting and preserves finite limits. So only little is missing towards it admitting a left adjoint by the adjoint functor theorem. When I say almost a left adjoint exists. And if it existed and preserved finite products, then this is exactly the setting of cohesion that we're in. And slicing over an object X is what we mean by local. At this point, let me give you maybe a slight warning, namely that there is a notational shift. So what is called J lower Schrieg here in our cohesion was not called J lower Schrieg, but in cohesion, J lower Schrieg was the functor which appeared on the top. So this is unfortunate, but I followed the original sources, and that is how they denoted their functors. Yeah. Okay, fractured structures themselves a priori are really difficult to construct, but luckily we have Lurie, who gave us this technology of admissible morphisms that allows us to construct fractured structures, which is something I want to introduce now. Definition, let C be an infinity category, then an admissibility structure on this category C is a collection of maps in this infinity category C, the so-called admissible morphisms. Satisfying the following properties, or constructed in the following way. Namely, equivalences are admissible. Then this condition 2 is very subtle and was a lot of work for us, or involved in a lot of work for us. So if we have an admissible morphism F from U to X and another morphism in the category C, then we can form a pullback, or we can try to form a pullback. And the condition that is that this pullback exists and that admissibles pull back, so that the pullback map is also admissible. Condition 3 is a backwards 2 out of 3 condition. So if we start with a commutative triangle such that G is admissible, then F is admissible if and only if H is admissible. And the last condition is that these guys are closed on the retracts of morphisms. Then we call C-add the white subcategory with admissible maps. And with this, we can now do the following. The definition 3.4. Consider an infinity site, so C equipped with a Rothendig topology. Then 1, our admissibility structure is compatible with the Grothendieck topology if and only if for every object in C and every covering stuff of this object, there exists a collection of morphisms over this object X, which generates a covering stuff. Such that L alpha is admissible and lies inside the initial covering system. Then a geometric site is a triple C with an admissibility structure on a Grothendieck topology such that our Grothendieck topology is compatible with the admissibility structure. The upshot of all this is that we can do the following. Let's consider a geometric site, C, Ciad, and tau. And denote the inclusion functor by J. Then a pullback notion of Grothendieck topologies makes sense. So we call J_ad as some pullback of this Grothendieck topology of tau via the functor J. And this allows us to define a pullback functor J upper star from sheaves on C to sheaves on the smaller category C_ad, endowed with this T_ad topology. And what did this bring us is the theorem 3.5 attributed to Lurie in his spectral algebraic geometry. Namely, let C, Ciad, and tau be a geometric site then there is an adjunction, these two categories. So there is a left adjoint to our J upper star functor called J lower shriek, such that J lower shriek induces an equivalence onto a fracture subcategory of use on C. That is, we now have a technology to construct many kinds of non-trivial fractured structures on C. So we have to construct some sort of admissible morphisms and show that they're compatible with a Grothendieck topology in the precise sense defined above. And then Lurie's technology immediately yields us a fractured structure. And this is what we want to apply. So now we can come to section 4. Cohesive and fractured structure in condensed math. These are two notions which were motivated to axiomatize and generalize the notion of topology. So naturally we want to ask, how are they related? And here's the first thing, which is good, I want to say. So here's the first positive result, lemma 4.1. namely condensed anima is local. So there exists the 3 adjunctions. And this is good. And to local, what's missing to cohesion is a 4 functor. So maybe it's already cohesive, and that would be really cool. Okay, but is it cohesive? Well, life is not always nice, and this is one of the situations where it's not. So no, it's not cohesive. But that's what we introduced fractal structures for. We want to replace cohesion by fractal structures. So the next mission was to find a fractal structure on condensed anima. And this was our first guess. Namely, we tried to take the following. We take Seehouse inch, which is the wide subcategory of compact Hausdorff spaces, those with the injective maps. And it turns out that this is an admissibility structure, which is really good, because to an admissibility structure, not much is missing towards a fractal structure. We just need that it's compatible with the Grothendieck topology, then we can apply Lurie theorem, theorem 3.5 in this talk. And for a very long time, we actually thought that this was the case, up until one day where we discovered that this is not true. So unfortunately, this admissibility structure does not define a geometric site. Which was one point where my math thesis was about to crumble apart. And so it was crumbling and crumbling, but up until a certain point, at least we had the following idea. So let's take a different category in the extremely disconnected spaces and consider a subcategory of this. So we take the wide subcategory, X is open together with open embeddings as maps. And we write cond open on for the sheaves on this category. And we have the following results, which led to the name of today's talk, theorem 4.3. There is a fractured structure on condensed anima. Given by cond on to cond open of on induced by the restriction filter. Okay, and let me sketch a proof of this. The goal is that we have actually found a geometric site, because then we can apply the theorem by Lurie to immediately get a fractal structure. And there are two things to check. One is that it's an admissibility structure, and the other is that it's compatible with the Grothendieck topology. So let's start with the admissibility structure. Admissibility. And there are 4 axioms to check, and I've written them out again on the right for you, so that you can see what they are again. Namely, the first one is that equivalences are admissible. Okay, but homeomorphisms of extremely disconnected spaces, they're open embedding. So this is okay. For part 2, we do the following. So we consider an open embedding of extremely disconnected spaces. And we consider another map of extremely disconnected spaces. And the question is whether it admits a pullback and whether the pullback is an open embedding again. So first of all, in topological spaces, we know that there exists a pullback given by the pre-image. And this is an open embedding. But now, these are all compact Hausdorff spaces. That means that S is compact, so f of S and T is also compact. So in particular, it's closed. And in particular, G inverse of f of S inside T prime is closed, but it's also open, so it's clopen. So this allows us to use a fact from extremely disconnected spaces, namely that clopen subspaces of extremely disconnected spaces are extremely disconnected again. Okay, condition 3 is quick to check. And condition 4 is the following. So if we have any open embedding of extremely disconnected spaces, and we take a retract of this map, then we want to show that the retract is also an open embedding. And this is done via some diagram chasing to show that the left square is a pullback square. And then you can apply point 2. The other thing to check is compatibility. And let me briefly write out what there is to do. So G alpha from S alpha to S, so consider a covering sheaf of some extremely disconnected space. Covering sheaf. This collection of G alphas. The covering sheaves in this topology were the finitely jointly surjective ones, so there exists some finite subset J prime of J such that the collection G alpha from the coproduct of these S alphas surjects onto S. Now we use very crucially that S is extremely disconnected. And those are the projective objects inside compact Hausdorff spaces. That means that there exists a section S of this map. We now denote by S alpha the restriction of S to S inverse of S alpha. And by I, S alpha, the natural inclusion of S alpha into this coproduct. Then you may see that this following collection of maps generates a covering and consists of admissibles. So the topology is compatible with the admissibility structure. And there we have it. This is a graphic structure on condensed anima. A remark about this structure It could still turn out to be the trivial fractal structure. So this is still a possibility, but it turns out that one can show that it's actually not. So this I lower Schrieg functor is not an equivalence of categories, i.e., the fractal structure we constructed is non-trivial. And two, to get back to cohesion, this I upper star functor, which was a functor from condensed anima and then restricted to condensed open anima, it does not realize cohesion. And both things can be shown by checking that I lower Schrieg does not preserve terminal objects. To end this talk, I want to briefly talk about an application that we set our minds on, namely in cohomology.
Sorry, can I ask something?
Yeah, sure.
Could you say a word about why the proof doesn't work for compact Hausdorff spaces? Why you need to go to extremely disconnected?
Yeah, so here we use that S is extremely disconnected so that there exists a section, and this is where we use extremely disconnected spaces because they are projective objects.
Okay, thanks.
Thank you for the question. Okay, the application is in cohomology. And I want to begin by the following fact, which Clausen and Scholze attribute to Dikov. And it's a fact that relates sheaf cohomology with condensed cohomology. So it says that if S is a compact Hausdorff space, then the sheaf cohomology of S at some constant sheaf of Z is isomorphic to the condensed cohomology of S at the condensed space associated to Z. And our goal was to reprove and hopefully find more spaces in which this is true. And we do the following, or we try to do the following. The definition: a corporeal space is an object inside the intersection of the following two essential images. So one can always take the restricted Uneda embedding and take a topological space onto its condensed anima. Or we can take our I lower Schrieg functor that we obtain from our fractal structure and an object in these two is called a corporeal space, what we call a corporeal space, because it's a space since it comes from topological spaces, and it's corporeal since I lower Schrieg gives us the corporeal objects. Then we show the following. If S is a space such that as a condensed anima is corporeal, then the sheaf cohomology of S is isomorphic to the to the condensed cohomology of S. And yeah, let me leave out the proof sketch, but the important part relies on the fact that we have gotten a fully faithful functor from our fractal structure, which is locally almost a cohesion where we had a fully faithful functor. And this is the key step in the proof. And to circle all back, corporeal spaces, they arise from this really abstract thing of a fractal structure, and they are really difficult to understand, and we really do not really understand what corporeal spaces look like. So this is maybe one goal, to understand what corporeal spaces are. Another direction could be to take a different approach, to take a different fractured structure and hope for one which is easier to understand. And this leads to our following problem. Namely, we saw in the admissibility structure, we always wanted pullbacks with admissible maps to exist and to be pulled back. And our question is rather, does extremely disconnected spaces have pullbacks where one leg is a monomorphism? And yeah, we don't know. This is a really difficult problem, seemingly. And we asked some fellows, like we asked Dustin Clausen, and he also didn't know, but he posed the following sub-problem, namely, does extremely disconnected spaces even have fibers? And this remains unanswered as well. So Anima briefly also talked to Peter Scholze, and he also couldn't immediately see a solution to this problem. So this is one of the open problems that might be helpful in our project to further understand this comparison of cohomologies. And at this point, maybe we circled back from our abstract stuff back to really point set topology, and remember that even point set topology and even not too abstract things can have difficult problems. And that ends my talk.
Thank you. Let's either unmute or send a reaction, and thank Xi for a great talk. So there is a question in the chat about if this generalizes to pro-Italic topos in general, where the pro-Italic topos of a point is the condensed topos, or even more generally, some weak projectivity introduced in Lurie's paper on ultra categories. And I think that was sent during your proposition 4.4. Please correct me if I'm wrong.
Okay, sorry, I don't know, because I don't really know these notions. Yeah, thank you for the question. But these sorts of generalizations are things that we are currently looking for, so maybe this could be a direction to think about. So yeah, we'll see.
Yeah. Is there any other questions?
So I see Catherine asks if locally compact Hausdorff spaces are corporeal, and the answer is we don't know. So they're really difficult to understand, and yeah, we don't really have a class of spaces where we know that they're corporeal yet.
Yeah, if anyone have more questions, then you're welcome to either just unmute or write in the chat. Is corporeal a more than compact Hausdorff?
Yeah, that we also don't know. So we also don't know. So really, we know about nothing about corporeal guys right now at this point, which is why it's still ongoing research.
Wait, can you say again? So you do know that the compact Hausdorff spaces are or not even?
Sorry, I didn't.
The compact Hausdorff spaces?
I think even these we don't yet know.
Okay.
So there is. Do you know for sure that it's not empty? That's a question.
Do we know this?
I mean, it contains all the representables, so it contains all the extremely disconnected spaces, at least.
Yes. Okay. Yes.
So since these are so hard to get your hands on, where was and maybe I've just missed an argument, where did the motivation for taking this specific intersection come from? Like, what's the intuition?
Okay, so the motivation was
Like, intuition.
So the motivation one was, so first we had a fractured structure given not on this side with extremely disconnected guys, but rather with compact Hausdorff guys, because we thought it would work, but it turned out it didn't. And then we tried to look for a different version, and this is what we ended up to, because extremely disconnected guys is a natural candidate to consider with condensed math. So we first looked for a fractured structure to work. And then for the application, so there are two things. One is we want to define sheaf cohomology, and we don't know how to do this if we're not in spaces. So that's why we take topological spaces. That's the first functor. And the second functor is the guy that comes from the fractured structure. So something, so these are objects of which we know some stuff. So, and then we take the intersection of the things that we want to consider and the things that we know something about. And this is why this currently is what we consider as corporeal spaces. But maybe there are better classes of spaces to consider in the future.
Okay, thank you. So I will stop the recording now, and then if anyone has more questions, you can ask afterwards. So thank you, Xi.